Great, thank you. Hi, everyone. My name is Tania, and I'm co-lead of the DEI team along with James, and we're really glad to see all of you here. So first, a little bit about our guest speaker, Dr. Strauss. They're a research scientist at the National Institute of Standards and Technology, or NIST, on detail to NASA Goddard Space Flight Center, where their work focuses on the development of techniques and instrumentation for experimental analyses of geological material during spaceflight. As a planetary geophysicist, Dr. Strauss studies how rocks and minerals from the moon and other planets record changing magnetic fields over billions of years. When not elbows deep in a magnetometer, they can also be found advocating for gender inclusive methods in studies of the space science workforce. Dr. Strauss, thank you so much for being here with us today, and you can take it away now.
Great. Thank you so much for having me. I'm really honored to be invited to speak in this series. Let me do the obligatory all right. Tell me if you can see my slides bit. I will assume from lack of complaints that we're good. All right. So today I'm going to be talking about a couple of different projects that I've worked on, that are connected by really one main theme. I work with a lot of really small data sets. And what I want you to get out of today's talk is that just because a data set is small doesn't mean it's not important. And often these small data sets are really what enable us to totally revolutionize our assumptions about the world around us. So first, a little bit of my background. I have a bachelor's in geology and a PhD in geophysics. And after my PhD, I did two postdocs, the first at Rutgers University, where I worked with Professor Sonia T. Koo, who actually is now a professor at Stanford, and the second in a functional nanostructured materials group at NIST. So now I'm a term research scientist at NIST doing a detail to NASA Goddard Space Flight Center, where I work on a couple of different projects. I primarily relating to calibration and benchmarking for instruments intended for spaceflight. So on the left, we have some surface roughness measurements from laser ablation pits related to potassium argon dating methods. And then on the right, we have a flux gate magnetometer and the ring core structure inside, where I'm working on understanding the materials that are used to construct these kinds of devices. So at Goddard, I work with this planetary magnetospheres group, which builds those fluxgate magnetometers intended to take magnetic measurements on space missions. And we're often looking at active magnetic fields, which tell us a lot about present day planetary interiors, as well as plasma environments. But what about planets that aren't actively generating magnetic fields today? And what about planets like ours, where magnetic fields change over time? Today, I hope to show you that a planet's history of magnetism tells us about its evolution, particularly the evolution of its interior, as well as surface and subsurface processes. So on terrestrial planets, these changes can be recorded in crustal rocks, and it's really rock level analyses that let us look at not just spatial patterns of magnetization, but how they've changed over millions and billions of years. Now, I come to this topic from a background in rock magnetism and paleomagnetism, which I'll define briefly here in case these are new terms. Rock magnetism is the discipline that asks, how do rocks record magnetic fields? What kinds of mineralogies are required? What kinds of mechanisms are operating inside the rock at a grain level to trap these records? Paleomagnetism, then, is the other side of the coin and asks, how do magnetic fields change over time based on records held by rocks? Now, these may sound like fairly broad headers for research disciplines, and the reason for that is that our field is united more by a collection of instruments than by any coherent research objective. Now, what this means for planetary science is with access to the right kind of instrumentation, we have the ability to answer all kinds of questions and apply our techniques to all kinds of materials from all over our solar system, or really anywhere we can get rocks. So today I'm going to be focusing on an example from my favorite place that we've got rocks from, the Earth's moon. The Apollo sample suite includes more than 2,000 rock and regolith and core samples returned to Earth by the Apollo astronauts. And we know from these samples that the moon used to have a pretty strong magnetic field, but it doesn't have one in the present day. So where did it go? In order to understand the moon's magnetic field, I like to put previous studies on a timeline. So here we've got years before present on the x-axis in units of billions of years, with the present day all the way to the right. And on the y-axis, we have paleo intensity, or the strength of the ancient magnetic field in microteslas. And please note that that's a log scale. Now, there are two different kinds of data on this plot. The filled shapes represent actual records of magnetic fields held in Apollo samples, and the open shapes represent maximum intensities those fields could have had based on the sample's recording properties, which I'll come back to in a minute. So I'm just going to show you some major trends in this data to help guide you through it. First, there's a generally recognized high field period from about 3.85 to 3.56 billion years ago, when the moon's surface field reached intensities that could have been comparable to the Earth's field today. A thunderstorm has just started outside, so if my power goes out, I will apologize for the interruption later. As we look further into the data, a few subsequent studies showed that there was no evidence for fields any stronger than about 4 microteslas by around 3.19 billion years ago. And from that information alone, we can start constructing this kind of generic schematic line. This is not quantitative, it's purely intended to help guide your eye. Now, a few years ago, another study came out finding a record of a 5 microtesla field in a sample that was dated to somewhere between 1 and 2 billion years ago. And last spring, another study came out showing that there was no longer any evidence for fields stronger than 0.1 microteslas by about a half a billion years ago. So from this collection of data, we can make some fairly interesting assertions about the behavior of the moon's magnetic field. Namely, it didn't just turn off overnight. We're looking at something with some incredible variation to it. In fact, there were likely 2 periods of decline in the intensity of the moon's field, one following the high field period, and then another one moving toward the zero field state that we observe today. So why do we care about these changes in magnetic field intensity? Well, changes in a planet's magnetic field tell us something about changes in how that field is being generated. So in this case, a bunch of different mechanisms have been proposed to explain the changes in the moon's magnetic field intensity over time, and I'm just going to mention a couple of the major ones here. So first, a few studies have proposed that the moon could have had a chemical convection dynamo or an impact-generated dynamo system, which would have been able to account for fields on the order of like 5 to 7 microteslas in intensity until maybe 3.5 billion years ago tops. Other studies have looked at precession-generated dynamos, where the interior and exterior portions of the moon could have been decoupled, and that mechanical stirring would produce the currents necessary to create magnetic fields. And that could have accounted for fields as strong as 100 microteslas, but wouldn't have lasted anywhere past about 2 billion years ago, depending which model you use. And still other studies have looked at, oh wow, it is raining cats and dogs out there, cool. Other studies have looked at thermochemical convection, which is the kind of dynamo generation system that we have here on Earth to get our magnetic field. And the idea is that by improving our understanding of the timing of the changes in the field, we can start to figure out which of these mechanisms could actually explain our observations. But you may be noting, there's really not very much data on this plot. And what that means is that we have to keep a careful eye on both possible methodological problems and small number statistics issues. So if we want to constrain the timing of field decline and start eliminating some of these candidate dynamo generation mechanisms, we have to ask a couple of different questions. First, did the lunar dynamo really decline after the end of the high field period, or could we be seeing an artifact of an older method or a sampling strategy? And second, if it did decline, what happened to it? In order to answer these questions, we need to work with samples that are capable of recording weak magnetic fields after 3.2 billion years ago. So this brings us to our paleomagnetism case study. I'm going to show you some experiments I did as a postdoc at Rutgers that we recently had published in the Journal of Geophysical Research Planets. For any geoscientists in the room, here is the obligatory map of my field site. This is the Apollo 12 landing site, and all 3 of my samples come from somewhere off the upper left edge of this image. I do have photos from where 2 of my samples were collected, but unfortunately not the 3rd, and this is something that I use to argue to my managers that we need to send more geologists to the moon, because we know to take a picture before we pick up the rock. And these are the 3 actual samples that I had the honor of working with. These are Apollo 12 samples 12008, 12009, and 12015. And each of the samples that you see here is about the size of the palm of your hand, though of course I received much smaller pieces of each of them. All 3 of these rocks are olivine vitrifier mare basalts, and our microscopy didn't turn up any evidence of shock effects, which suggested to us that they were likely magnetized through primarily thermal processes as they cooled through some critical temperature, or thermoremnant magnetization. We determined new argon-argon ages for 2 of these 3 samples, and the first ever argon-argon age for the third, dating all of them to right around 3.1 billion years ago, just as we had hoped. And because these are rocks that we know to have been rapidly cooled and they have fine overall grain sizes, we hope that they might contain some good magnetic recorders, with the understanding that finer grain sizes often correspond with better magnetic recording properties. We were particularly interested in these bright grains that turned up in our reflected light microscopy, which we thought might be the iron nickel grains suggested by previous studies of some adjacent basalts. So we did our analyses in the Rutgers Paleomagnetism lab, which has been largely relocated to Stanford. What you're looking at here is a magnetically shielded room. So it's a room inside a room, and it has its own 4 walls, ceiling, and floor that are insulated with multiple layers of steel and mu metal, such that the Earth's magnetic field inside is attenuated almost to zero. So when you walk up a couple of stairs and you leave your phone and keys and other magnetic paraphernalia outside the room and go through this door, you see our magnetometer. This is a 2G squid rapid system that is capable of handling a large number of samples at once, but also running some pretty complex experiments. So if you step onto the platform behind the instrument, you can see the actual instrument stack. At the top, we have a degausser, which can apply alternating magnetic fields to demagnetize a sample. Then we have a zero region, and at the bottom is our measurement region, where we can measure in both X, Y, and Z axes, which is pretty cool because we can take 3-dimensional measurements of our 3-dimensional magnetic signal. And you can also see our sample handling system. There's this clear quartz glass tube that you might be able to make out, and that can exert a vacuum to hold a sample on the end and move it up and down through the instrument stack, such that you can pre-program what kind of experiments you want to do, and then you don't have to sit there and like press a button every 2 minutes yourself. So with that, I'm going to jump right into some results. The first question we asked was, did these samples record a field? And in order to answer that question, we did an experiment called alternating field demagnetization of natural remnant magnetization, or AFD-mag of NRM, which means we applied alternating magnetic fields of progressively increasing intensities in order to stepwise remove or demagnetize the magnetic signal that our samples came into the lab with. Now, paleomagnetists plot the data from this in kind of a weird way, so I'm going to show you how we plot it, and then I'll show you my actual results. What we're trying to do is plot a 3-dimensional magnetization vector in 2-dimensional space. So we start by plotting a horizontal projection. We have our, oh my goodness, we have our east axis here and our north axis. And when we apply magnetic fields at stronger and stronger intensities, we progressively remove the signal and can see that data trending towards zero. Now, if we plot a vertical projection of the same vector, now we have our z or up axis on top, and that looks a little bit like this. Same deal, as we apply stronger and stronger fields, we're removing magnetization. Now, when we combine these together, we get what's called a Zeigerfeld plot. And this is our total 2-dimensional projection of a 3-dimensional magnetic vector, and that looks a little bit like this. Now, here's what my actual data looked like. If you are looking at this and thinking, wow, that looks a lot like noise, you are correct, at least once we remove this low coercivity component, or a component that can be taken off with fairly small magnetic fields. And this is consistent with the kind of overprint that a lot of Apollo samples have picked up just by like hanging out in the Earth's field for 50 years. But once that's removed, what remains is in fact statistically indistinguishable from uncooked spaghetti. From cooked spaghetti, that would be an important distinction. And from this, we unfortunately could say we were not able to retrieve a stable high coercivity magnetization from these samples. So that's a little bit of a bummer. But then we asked, how weak a field could they have recorded? Now, this is an important question because the paleomagnetic techniques that were used during the Apollo era to look at these kinds of samples were not always able to differentiate between samples that did not record an ancient magnetic field versus those that had poor remnants or poor recording properties, and samples that had experienced a strong paleo field versus those that had picked up some spurious remnants on Earth. So to get at these differentiations, we did some paleomagnetic fidelity experiments. To determine the minimum field that these samples could record it, and thereby their fidelity limit, we performed a series of laboratory experiments where we essentially applied an artificial magnetic field of a known intensity to each sample to simulate the processes it had gone through to get magnetized, and then attempted to get back a record of that field using the same methods I just showed you, the hope being we should see a one-to-one relationship between the applied field and the retrieved field. So here are some of our results. In the leftmost plot, I've got the applied laboratory field on the x-axis and the retrieved paleo intensity on the y-axis, and our data should be clustering around this one-to-one line I've got in dashed gray here, but it's kind of hard to make out what you're seeing there. So if you look at the second plot instead, now I have the applied field on the x-axis and the difference between the applied field and the retrieved field on the y. And if we use this 100% difference threshold from some previous studies, we find that two of our samples gave us back good records of magnetic fields as weak as 7 microteslas, and one sample gave us back records of fields as weak as 4 microteslas, which is pretty weak. So from this, we can then say our methods would have been capable of retrieving capable of retrieving records of a weak magnetizing field if it was any stronger than about 4 to 7 microteslas, which you may recall from like 2 slides ago, we did not do. So with those experiments out of the way, we can now return to our timeline and in combination with our new argon-argon dates, place our samples into their correct position, essentially quadrupling the amount of data available right around 3.1 to 2 billion years ago. This is really essentially a replication study because we came out with something in very nice agreement with previous work, which I get really excited about because that lets us think back to the small number statistics issue and ask a question like, is this decline statistically significant? Now, we wanted to compare the paleo intensities of samples from the high field period with younger samples from the initial period of field decline, because the fear was that these two data sets could have come from the same initial distribution of paleo intensity values. Prior to this study, that null hypothesis could be rejected with a p-value of 0.0152. And when we add our 3 samples to this calculation, we can improve that by an order of magnitude. So with that, we can say with much more confidence that there was in fact an order of magnitude decline in the intensity of the moon's magnetic field following the high field period. Now, traditionally, this would be the part of the talk where we would go back to thinking about mechanisms to explain this decline and start digging into different models, but I'm not a modeler, I am an experimentalist, and instead I want to talk about the question that had been bothering me the whole time, which is, why were our samples such good recorders? Why were we able to replicate such a tight limit on the strength of the moon's field? So this is the table that I put together as we were building that timeline of previous studies of lunar paleo intensity. And it's kind of hard to see here because it's small, I know. But the first column is giving sample identifiers, and the third column is giving paleo intensities in microteslas. And I really just want to draw your attention to the intensities that are showed here with less than signs in front of them. These are actually paleomagnetic fidelity limits, indicating the maximum strength the field could have had when each sample formed based on the minimum field it would have been able to record. And you'll notice that there's quite a range of fidelity limits reported here. So some samples could record fields weaker than 1 microtesla, while others could only record fields upwards of about 75 microteslas. So I was really interested in this variation because our 3 samples exhibited extremely good, but not the best, magnetic recording properties. So we can use these 3 samples as kind of a case study to help us talk about the magnetic mineralogy of lunar rocks and the ways that they record fields. For a little bit of perspective, early studies of Apollo samples indicated that their ferromagnetic mineralogy was dominated by metallic iron, and that understanding was later expanded to include both iron metal and iron alloys with nickel and cobalt and other trace contaminants. And at that time, the most commonly found form was recognized as camosite, which is a body-centered cubic iron-nickel alloy mineral. Now, over the past decade or so, improved methods for the assessment of paleomagnetic fidelity have been accompanied by more detailed analyses of magnetic carrier minerals, including non-magnetic analyses that let us do things like differentiating iron-nickel alloys by mass fraction. For instance, we can now tell camosite, which is a low nickel alloy, from martensite, which has a higher nickel content, which is pretty cool. All that being said, when we compare these kinds of assertions that I just made to what's been going on in terrestrial paleomagnetism research for decades, it's pretty clear that lunar paleomagnetism has a little bit of catching up to do. And although various magnetic parameters in lunar rocks have been surveyed to various extents, we're still kind of working on modernizing our approaches to experimental methods and the strategies that we use to interpret magnetic characterization data. Now, my goal here is really to try to advance astromaterial magnetism past simple expressions based on bulk mineralogy and toward a more complex and nuanced exploration of grain and sub-grain scale dynamics, especially with respect to magnetic domain behavior. So we can think about a magnetic grain as subdivided into these little compartments that we call domains, each of which contains a single magnetic moment. The idea is that smaller grains with fewer domains are typically expected to behave more predictably and to hold records of magnetic fields for longer. But how small is smaller? How long is longer? The first question we really wanted to answer here was, what are the metallic grains that we turned up during microscopy? So we did some EPMA analyses at Rutgers, and what you're looking at here are qualitative elemental X-ray maps, which we collected in addition to obtaining quantitative points from individual grains. So if we look at the third column, where the background is kind of this dark navy color, I have iron in blue and nickel in green. So we can say fairly confidently that we did find some iron nickel grains, which is very exciting. But I want to point out a few other major things that we noticed as we were searching for them. First, we found grains with different iron nickel ratios in each sample, and we were able to identify both camosite and martensite. In fact, we mostly found martensite, while other studies of different basalts have found mostly camosite, which is kind of interesting. We also found that many of these iron nickel grains are not homogeneous, so you can see some compositional gradients in the grains that I'm showing here. We also observed some bright submicron sized grains that were unfortunately too small to acquire quantitative points from, but from all of that, we can say that we observed multiple sizes of both camosite and martensite, which is pretty exciting. So some previous studies have also suggested that association with troilite, which is an iron sulfide mineral, might be an indicator of paleomagnetic fidelity in lunar basalts. So we went looking for troilite per this fourth column, where now I have sulfur in pink and iron in blue, but we didn't actually find any. So in general, I would say that troilite may form through processes that also produce submicron iron grains, but it's definitely not a requirement for high paleointensity fidelity. Okay, that's our non-magnetic analysis. Now, what's actually happening when we apply magnetic fields? To try to answer this question, we used a technique called hysteresis, and hysteresis experiments have been kind of a bread and butter technique for rock magnetic analyses for more than 50 years. In a hysteresis experiment, we take a sample at room temperature and apply a magnetic field of increasing intensity in one direction and return that field to zero, and then apply a field of the same intensity of the opposite direction, and then bring that back to zero, all while measuring magnetization. The idea being that the way that magnetization responds to the strength of an applied field and whether there is a lag tells us something about the composition of the sample. So here are three representative subsamples that we ran these analyses on. On our x-axis, we have the applied field in Teslas, and on the y-axis, we have our magnetic moment. And you can see our raw data in orange and corrected data in blue. So I've also pulled out some coercivity and magnetization parameters, which are typically used to define the shape and size of each loop. And this is what lets you start comparing samples to each other. Now, this is really where it starts to get interesting, because since hysteresis loops have been standard for so long, this lets us think about comparing our results from just 3 samples with data that goes all the way back to the Apollo era. So what I'm showing here is a day plot, and these are typically used to understand how the hysteresis parameters of different samples relate to each other. On our x-axis, we have remnant coercivity divided by coercive force, and on our y-axis, we have saturation remnant magnetization divided by saturation magnetization. And the hope with a day plot is that samples with better recording properties should plot toward the upper left, and that should correspond with better magnetic fidelity. So what we built is, to our knowledge, the largest published compilation of hysteresis parameters from Apollo samples to date. Each data point that you see here represents one sample or subsample from literature, sorted by bulk rock type as kind of a first pass. And the data from our study is shown in orange squares. I've also included these gray dashed lines, which indicate domain state regions from the original day plot that are sometimes used to calculate grain sizes. Now, I'll note the position of samples from a few recent studies on this figure just by way of example, and you can kind of get a sense from this handful of points that the general trend we're hoping for seems to hold. We see better lower fidelity limits as we move toward the upper left of the plot. However, there's a problem when we start to look at the domain states from which, again, grain sizes are often inferred, which is those dashed lines do not actually exist. The guiding domain parameter ranges were originally developed for magnetite, Fe3O4, and not only are they not applicable to other types of magnetic minerals, but studies of terrestrial minerals in the last few years have shown that they were likely fairly imprecise tools in the first place. So we'd rather not encourage overinterpretation of our actual data based on those ranges. And what that really means here is I'm very proud of the data compilation that we've assembled, but I caution against the use of plots like these to discern specific domain states or grain sizes of magnetic minerals in lunar samples, mainly because not a single one of the samples shown on this plot contain magnetite. Okay, so we've talked a little bit about grain size, and long story short, we see interesting mismatches between petrographically observed grain sizes and those that are often inferred from magnetic measurements by way of domain states. And in our samples, we observed these two different populations of iron nickel grains that we wouldn't have been able to differentiate from hysteresis experiments alone. We also took a quick look at the association of iron nickel grains with other minerals, and I didn't mention magnetic anisotropy, which could also be important. And I'm currently working on digging into compositional variations among iron nickel alloys, which I personally think is really intriguing. We've had some discussions about whether it would be informative to calculate theoretical domain state regions and day curves for iron minerals, which wouldn't tell us anything about grain sizes without some experimental grounding, but could give us a sense of how far off we currently are from reality. So where do we go from there? The data that we use to build our day plot is freely available at the NIST data repository, which you can find at this URL, as well as in the supplemental information for the paper that we just published. And if you're interested in these kinds of questions or anything that I've mentioned about lunar magnetic mineralogy, I highly encourage you to go play with that data yourself. It's really just a big spreadsheet, and see if you can find any patterns that we haven't identified yet. I also have been trying to encourage our research community to collect more first order reversal curves and make them a routine part of lunar rock magnetic analyses, just like we do for terrestrial analyses. So a first order reversal curve essentially fills in the empty space in a hysteresis loop, and they're able to give us a lot more information about different populations of grains and the interactions between them, as well as information about potential anisotropies. Now, something like half the data in the day plot was collected before this technique was even invented, so this isn't just about future studies of samples we haven't analyzed before, but also about thinking about our archive of information. I'm showing an example here from the paper I mentioned that came out last year, just so you have some sense of what this can look like. The clast on the left has this horizontal ridge that extends to fairly high coercivities, and that suggests the presence of single domain and pseudo single domain grains, which are quite small. While the glass on the right, in addition to that central ridge, also has this cluster at low coercivity values, and that suggests the presence of larger multi-domain grains. And I can tell you all of that totally independent of a day plot, which is pretty cool. So if you have zoned out at any point here or gone to check your phone, I'm going to summarize everything you've just heard in about 2 minutes before we move forward. What happened to the lunar field after 3.56 billion years ago? Well, we would have been able to retrieve a record of that field if it was any stronger than about 4 to 7 microteslas. However, we did not retrieve a stable record of a magnetization consistent with that kind of planetary field. Therefore, we find no evidence for lunar surface fields any stronger than 7 microteslas at about 3.1 billion years ago. And as a reminder, that's roughly an order of magnitude drop. Now, in order to explain this, we need either multiple mechanisms of field generation or a bistable dynamo that could have sustained field intensities in a high field and low field state before collapsing. We think that the most likely candidates here are a combination of a precession dynamo and thermochemical convection. The idea being that a precession generated dynamo could have accounted for the strong fields observed during the high field period until the increasing distance between the moon and the Earth was sufficient to remove the moon from the gravitational state necessary to produce the current to produce the fields. And then that would give way to an underlying thermochemical convection system produced by core crystallization, which could account for the weak field period until collapse for the present day. But in fact, there could really be a whole lot of complexity in field behavior that isn't captured by this data at all, which I think is extremely exciting. Then we also found evidence that the evidence for these processes is held by a variety of iron nickel minerals. And these systems are really way more complex than we thought. We're just starting to understand how they really work. So anyway, one day while I was supposed to be writing up these results, I was on Twitter, as one does, and I saw this grad student that I follow in astronomy tweeting about some papers that they were very frustrated by. And they had noticed this sort of odd, insidious trend in studies of gender and gender equity in astronomy and related fields, where these papers would have some sort of like X% of women do this thing and Y% of men do that thing, and then there would be an asterisk. And the asterisk would take you to a footnote. And the footnote would say something like, we acknowledge that non-binary people exist, but we choose not to talk about them in this study because they don't fit into the binary model we've already chosen to use. Or we acknowledge that non-binary people exist, but we choose not to include them here because we do not feel that they are statistically significant. So this grad student, who is a non-binary person in space science, was rightly frustrated by what they were reading. And a bunch of other grad students chimed into this thread and found more examples. And I, being me, waded into the replies and sort of half-jokingly said, do you think they would take us seriously if there were enough of us to write a white paper? Long story short, we wrote 2 white papers, and this is, I think, why we are actually talking today. On the left is our white paper for the Astronomy and Astrophysics Decadal Survey, and on the right is the one from the Planetary Science and Astrobiology Decadal Survey, essentially looking at these kinds of weird, insidious, harmful methods that studies of gender in space science often end up using, and offering some suggestions on how to not do that. So I want to just summarize some of our main points from these papers. The first finding, if you can call this a finding, is that efforts toward gender equity in space science primarily target and benefit cisgender, white, heterosexual, abled women. That is a very narrowly defined set of criteria, and anyone who does not check every single one of those boxes is not benefiting from these efforts in the way they were allegedly intended to. Second, space scientists, and I include myself in this, are not experts in gender studies or social science. And as a result, a lot of them end up using methods that are sloppy at best and harmful at worst. And I mean that with respect to both the empirical qualities of their analyses, the statistics that they are running, and to the ethical qualities of the studies they end up putting out. And a third point, there are non-binary and trans people in space science and related fields, and we want to be included. So in these papers, we essentially summarized some of the problematic approaches to gender that we found in previous studies of space science and the space science workforce and student body. First, a bunch of these studies treat gender as observable, by which I mean they attempt to acquire gender information by means other than participant self-identification. And this often takes the form of things like first name scraper algorithms or looking at photos, or even a couple of instances of asking volunteers at a conference to perceive and write down others' gender in real time. Now, the big problem here is that these methods result in misgendering and erasure, especially but not exclusively for non-binary people who end up being either misclassified or discarded from the dataset. And I also want to note that many of the first name scraper algorithms in use for these kinds of studies are trained on datasets of quote unquote Western names, which means anyone whose name doesn't show up in that dataset gets their data thrown out too. So it's like they went in trying to do a sexism and like accidentally got a bonus racism. Second, most of these studies treat gender as discrete categories that are presumed to be stable and coherent across populations, within individuals, and over time. And most of these studies require gender to be either binary, male female, or discretizable. Choose one of this finite list of options. Now, the problem here, aside from that not being how gender works, is that this is reducing members of a category to interchangeable data points, and that denies people authority over how they're being represented. Now, a third category is to treat gender as statistic, and this is the asterisk thing that I just mentioned. While we recognize that gender is not binary, we do not include non-binary people in our analysis due to lack of statistical significance. Now, when I read something like that, and I got a little bit frustrated about it, I think to myself, okay, these people don't know how gender works, and they also don't know how stats work. I don't have to work with them. That's fine. I have a job. I can get over it. But the concern is that when a student or a grad student or a more junior person reads something like that, the message that they are receiving is, we do not include you here because there are not enough of you to count. And my fear is that someone who gets that message is not going to want to come back to this field. The problem here is really that these methods are making statistical significance the determining factor in who matters, in who counts. The other problem is that they are also wrong, and I'm going to come back to that on the next slide. A fourth category of methods that we added for the planetary science version of this paper is treating gender as inconsequential. And this often takes the form of gender groupings like women and non-binary people, or women plus, or female non-binary and female identifying people. And the problem here is that non-binary people are not a subcategory of women. And a lot of these phrases also attempt to separate transgender women from cisgender women and incorrectly imply that they are not women. And let me say that a little more clearly, trans women are women. So with that, I want to show you some of the new findings that we had from the Planetary Science Decadal Survey, where we were provided some unpublished data from a few recent surveys of the planetary science workforce. The Goddard Climate Survey, which is run at NASA Goddard Space Flight Center by the LGBT Advisory Council, found in 2020 that 0.5% of their respondents identified as neither male nor female. The Division for Planetary Science at AAS ran a workforce survey that in 2019 showed that 1.1% of respondents identified as non-binary or another identity, and that number includes students. And the Space Science in Context Conference, which was run last March, I believe, provided us with some information about their attendee feedback surveys that were run at the end of the conference, where they found that 13% of respondents identified as non-binary, and 10% of presenters and speakers expressed a preference for non-binary pronouns, including but not limited to they, them, theirs. So from all of this, we can conclude that there's like a lot of non-binary people in space science. And if I can add one more piece of anecdata on top of that, I actually run a networking group for non-binary people in space science. And last time I checked, there's like 58 people in there, which means I personally know more than 58 non-binary people in space science, which is a lot. So with that, the recommendations that we submitted to the Planetary Science Decadal Survey were as follows. First, do not gather gender data through any means other than voluntary self-identification, and absolutely do not use automated gender classification methods. Second, if you want to study marginalized people in space science, you need to employ actual social scientists, not planetary scientists like me who think data is fun and do this as a hobby because it's interesting, but real trained social scientists. Third, our field really needs to work on shifting our focus from women to people of marginalized genders. And I don't mean by changing the names of groups or events or series or whatever. I mean by taking a real critical look at whether these groups and series and events and spaces are genuinely serving the people they were ostensibly intended to, or if we are ending up ostracizing the people that we were meant to help. And finally, we cannot let suggestions or platitudes satisfy us, because the only path to changing our field and improving our disciplines is action. What this really means, and especially when I give this talk to funding bodies, is material support for the most marginalized and vulnerable members of our communities. And that can mean jobs or internships or co-authorships or collaborations, and funding. Real, genuine material support is the first step on a route toward change. So with all of that, one of the things that I was kind of asked to talk about when I was invited to give this talk was the question of how we can better support non-binary people in STEM. I am not actually an expert on this. If you've got specific questions about specific issues in your departments, I'm absolutely happy to go into that in the Q&A. But otherwise, I'm really just a non-binary person who is in STEM. That said, I think a lot about normalization, and I think a lot about visibility. And what I really want to note here is institutional culture produces institutional climate. When our field and institutions create a culture where we treat trans and non-binary people as acceptable casualties in a push for gender diversity, we are creating a climate where they do not feel supported and cannot be their best selves, and that is unacceptable. And more than that, when we talk about support and inclusion and equity in STEM more broadly, we have to remember that there are zero acceptable casualties. I also want to point out that I can really only speak to my own experiences here, and LGBTQ+ in STEM spaces, which are the contexts where I usually get invited to talk about this research, have a huge whiteness problem. But there are a lot of people out there, tons of people who are doing incredible science who are not me. And so I wanted to at least include a shout out to a few great organizations here, because just because I can't speak to those experiences, it doesn't mean you shouldn't benefit from hearing about them. 500 Queer Scientists is essentially an outlist for queer and trans people in various parts of STEM. Black in Geoscience includes planetary science and exospheres, and Black in Astronomy covers astronomy and astrophysics and related fields. And they both maintain incredible lists of profiles of folks who are doing just some amazing research that you should totally look into. And with that, I will leave up some takeaways. I have to say thank you to the CAPTEM program for sample allocation. It was a huge honor to work with Apollo samples as an early career researcher. I also want to thank Professor Tiku, who may or who may not have showed up for this talk, for being a great postdoc advisor and creating an environment of support for all the research you saw here today, whether or not she knew I was doing it. I also want to point out that my contact information is located in the upper right corner of this slide. Please feel free to send me follow-up emails or find me on Twitter. I love yelling about moon rocks. And I also want to close by saying to any non-binary and trans students who are listening to this either live or when a recording goes up somewhere, my virtual office door is open to you. And with that, I am happy to take some questions.
Thank you so much, Dr. Strauss. Let's give a virtual round of applause. Sweet. That was a very engaging talk. I personally learned a lot. Does anyone have any questions before we turn the recording off? You can feel free to either raise your hand or you can also just unmute yourself and start speaking.
Mine is more just on the sides. I'm Jack. I'm actually part of SSI. I work at EHS with this at the board meeting and EM pronouns. With the magnetically shielded room, like how sensitive is that instrument? Like how low does it go? Like how much effect is, like you said you left the phones outside, but then there were the computers in there. Like how much effect are you picking up from that?
Yep. So to get you an actual sensitivity limit on that instrument, I'd have to go dig a number out because this was a couple years ago. But I can say the actual reason that we ask people to leave phones outside the room isn't just your phone is magnetic. It's your phone is moving through space and we don't know where it is at all times. The computer is in a fixed location and we pick that location when we set up the instrument. But if someone comes into the room as a guest, for instance, and their phone is in their back pocket and they accidentally back into something, I knew somebody in grad school whose rocks might have gotten remagnetized because he was like listening to music in front of the instrument and his phone was too close to where something was passing through. So it's really, we're just trying to prevent those kinds of incidents by asking people to leave magnetic equipment outside. That being said, I should also note the magnetically shielded room is not a Faraday cage, which means your phone will receive calls in there. And that's part of why the temptation comes in to, if the phone is there, you will be interacting with it.
Gotcha. Interesting. Thank you.
Hi, I'm Laura, she, her. I'm in the geophysics department. Sonia is also a great professor. I agree completely with that. But I had a quick question. I was wondering, for the process of analyzing your samples, do you destroy the magnetization during analysis, or is there like a chance to go back to old samples and like apply new methods to trying to eke out what the magnetization on old samples is?
So the short answer is we are irreversibly removing the magnetic signal. And you can think of it kind of like, oh no, I'm going to date myself. It's like when you record over a VHS tape or a cassette, because we are changing a magnetic signal that's held by those magnetic domains, those magnetic moments, and once it's gone, it can't come back. This is why we use very small pieces of our samples, and we're also cutting multiple oriented subsamples of each main sample we use, so we have the ability to make sure that we are replicating everything that we say. But any sample that has been overprinted by some additional process, like being cut with a circular saw, or has been analyzed through these particular methods, we can't do it again. That's why it's so important for us to get it right the first time. That being said, the Apollo sample suite is huge, and all of these samples that previously have been analyzed, there's more of that sample. If the sample is this big, we're working with that much of it, and there is a lot of rock left that we can get useful magnetic information out of, even after other people have done chemical analyses and physical analyses and microscopy and whatnot. As long as the magnetic signal is still there somewhere, we can probably get something cool out of it.
Ahmed, I see your hand raised.
Hi, thank you so much for the talk. So I had one question about the kind of two regimes you mentioned with the paleo intensity data. I know you mentioned that you prefer to go on like the experimental side instead of the models, but like just for my own curiosity, could you talk a little bit about kind of the models people have come up with to explain why there is that like sudden drop off?
Yeah, so the modeling studies are coming from a lot of different directions, and a lot of it goes into your sort of initial assumptions about what the interior of the moon looks like today and what it looked like as it was forming. And so this is where you get differences between like thermochemical convection with and without core crystallization, or straight up chemical convection without a thermal component. And there are a lot of different factors that go into differentiating these major models. So when I look at the precession dynamo, that's one that I find a little bit easier to understand because it ends up being more simply about the rate at which the moon was moving away from the Earth after the proposed giant impact hypothesis, where a big chunk of the moon was whacked off to merge with this other. So as the moon is reaching some distance at some speed, the idea then is that the physical precession that's occurring is no longer being driven by the Earth's gravity, and it can essentially stabilize, allowing that kind of current that generates the field to collapse. So we're looking at like really large scale systems here. But if you want a really good rundown of these models in a much better way than I can give, there's a paper by Ben Weiss and Sonia Tiku from 2014 that gives like a really nice couple of page summary of all of the major modeling strategies for these kinds of dynamo experiments.
Was there another hand raised during that? I think I missed it. No? Okay. Well, I have a question. So I know you were mentioning that you got access to actual moon rocks, which is really cool. And I was wondering, can any analysis be done by rovers on the moon or Mars? And then will there be samples coming back in the upcoming Artemis missions? And is that going to have a significant impact on this field?
That is a great question that I have literally had meetings about in the past 2 weeks. So short answer, paleomagnetism is not a major priority for current planned missions. And by paleomagnetism, I mean doing the kind of analyses I'm showing where we have a sample that we are getting information out of. There are other conversations about bringing magnetometers along on lander missions so that we can look at crustal anomalies, which are a little bit large scale, rather than looking at these sort of small sample records. Part of the reason for that is that the technology that we use, this SQUID, the superconducting quantum interference device magnetometer that lets us get access to these very weak fields, has to be run in cryogenically cooled conditions. And that is a nightmare to do in space. People just don't even want to talk about it. That being said, technology is developing all the time, and it would be very cool if someday we could do this kind of thing in situ, like we do like in the field on Earth. There are rock magnetic expeditions that go drill from cliff faces and can do analyses in the field, or like the IODP ships have onboard magnetometers, and they can do these analyses in the middle of the ocean, which I think is really cool. But the Artemis missions you mentioned, my understanding of the sample collection plan for the Artemis missions is like a little bit shaky, so don't quote me on this in an official capacity. But my understanding is that the Artemis astronauts are likely going to sample, much like the Apollo astronauts did. And there's a lot of development going into the sort of geology tools they're going to be bringing, hammer and drill and core tubes and things like that. And the paleomag stuff is not part of what's being targeted, but I have had some very productive conversations about how we can make sure that the samples that are collected for other priorities are still useful to the paleomagnetists. So I might not get a beautiful oriented drill core or whatever, but excuse me, I can at least ask for something that was not remagnetized by being processed in a certain way. Or we're thinking about things like if the samples need to be shielded in a particular way when they are picked up and put in a bag and put in a craft and brought back to Earth. So that was a long way of saying, hopefully we'll get more and better and interesting data out of this. And even if we are not the first priority, working with these kinds of samples have made paleomagnetists very good at getting information about samples that have been through a lot. If you hear crunching, that's my cat. Sorry.
That's really interesting. Thank you. Does anyone have any more questions before we turn the recording off and go to the unrecorded section? If anyone would like to ask some unrecorded questions. Yeah, Tania.
Yeah, I just had a question out of curiosity. Like, what is the process like of getting a sample from the actual moon rock?
It is a process. So the samples that I worked with were originally requested by Sonia when she was a PhD student, Professor Sonia Tiku as a PhD student, through the CAPTEM program, which is it's basically the astromaterials curation program out of Johnson Space Flight Center. And NASA's Johnson collection is a public resource, but that is where all of the samples live, essentially. So these samples were allocated to MIT, and for MIT to get them, they had to have a lunar safe in order to store them, which is defined as some kind of safe that's like attached to a wall with screws, so you can't just walk away with it. And it has to be, I think, behind 2 different key accesses. So it's like the key to the safe and then the key to the room. And you have to have some form that you submit about who has which key to what thing. And all of this has to be inspected by, I believe, a campus security officer with NASA authorization, which is apparently a thing that you can have. You can be a NASA security officer on a campus. And then those samples were at MIT for 5 years or so in that shielded room. And then when it was time for me to take them to Rutgers to do analyses, the easy way to do this is you can't, well, okay, not easy, but to move samples between facilities, you have to mail them by USPS back to Johnson, and then Johnson will mail them to the next person, or you can hand deliver them. And that's what I got to do as a postdoc at Rutgers. There was a form that Sonia filled out about transferring samples from one institution to the other, and there was a line in there about if anything, if the moon rocks get stolen or do not get to their destination, you will go directly to federal prison. Do not pass go, do not collect $200. And if anything happens to you in transit up to and including murder, you cannot sue NASA. So I, having had a driver's license for like 2 months, drove from New Jersey to Boston to pick up these moon rocks in we had a magnetically shielded briefcase, and I was like, should I handcuff myself to the briefcase? And I was terrified I was gonna like leave it in a rest stop because I couldn't just leave it in my car, and brought it to Rutgers, and then got to do all the experiments that you saw here today. So that was the most stressful road trip I have ever done in my life, and the longest possible answer to your very simple question, but it was super cool, and I would absolutely do it again.
Honestly, from what I'd heard of NASA samples, that's actually shorter an answer than I expected for what you need to do to get a moon rock.
I didn't have to request these in the first place. Like the CAPTEM forms are a whole, I know some folks who work in curations at JSC now, and it is extensive, and also I understand why. Like a lot of care goes into how these collections are managed, and this is so that people like me, 50 years after these samples were collected, can still know exactly what I'm getting when I sign up to do these kinds of experiments.
Yeah, it's incredible.
Yes.
I have another question about the second half of your talk before we turn off the recording.
Sure.
So do you see that there tends to be in surveys of companies or institutions that the survey show fewer non-binary people than at conferences or other settings? And do you think that there's ever situations in which non-binary people would not mark or just mark man or woman if they want to stay closeted at work?
Yeah. So I am making a bunch of assertions here based on a small amount of data. This is the theme for today. I, prior to the stuff that you saw here, was doing some work with the Federal Employee Viewpoint Survey, which is a study of the demographics and workplace experiences of federal employees. And they had just introduced a question about gender identity. For the first time in 2018, this survey asked, are you transgender, yes or no? And that was the first time ever that we had data on the number of trans people working for the federal government. Now, this was really interesting to me because I was just sort of like figuring out my stuff and goofing around with data, and it was all public and I thought it was fun. And then I started to have conversations with other people researching these topics, like survey design and studies of LGBTQ plus people of various gender identities and sexual orientations. And a generalization that I came away with there is that all of the numbers that I show you are a floor, not a ceiling, because almost universally, queer people and trans people will choose not to identify themselves on surveys because they do not perceive it as safe. And in a lot of cases, that is a reasonable presumption. So we get into these conversations in survey design spaces about how to make it clear to people who take the survey that their data is going to be anonymized in ways that are appropriate and are not going to inadvertently out them through combination with other demographic factors or things like that. When it comes to the differences between like workforces and conferences and student bodies, this is like everything I'm about to say is not peer reviewed. This is my own take on a little tiny pile of data that I've seen. I have to give all these caveats because I work for NIST, which is literally a metrology agency. But the theory that we are currently operating on is that we see higher numbers of non-binary people identifying themselves on the feedback survey for this conference I showed than on the workforce surveys, because this particular conference did a lot of legwork to improve the diversity of the speakers and the attendees and to create a space through its materials and its website and its advertising and the programming they put together and the featured speakers to attract an audience that is not necessarily representative of what you get when you do a workforce survey at a place like Goddard. So it's possible that their numbers are quite high compared to what you would see for like all of space science, but also that may be an indicator that they are doing something right.
That's really interesting. Thanks for sharing that with us.
Sure thing.
Yeah, Ahmed.
I also had a question about the second half of your talk. So one thing that I feel like, I'm with the physics department here at Stanford, and just a little anecdote to like help set up the question is, so in the past kind of like year here, our African American Studies department has been trying to move from being like a program to being like an official department in the university. And a big part of the push to try to do that was to try to get, support from other departments that were more established to say that, this is work that we recognize, that we really value. We wish that our colleagues and our peers like had the opportunity to do it as a department rather than as a program. And that was something that they were just kind of asking of all of the other faculty in the university, with the understanding that like the work that they do kind of motivates and helps and can benefit the types of things that a program like physics might want to do, especially when it comes to surveys and trying to make the program like a better place for students, of different genders and different races, just in general. And so, what actually ended up happening though is that very few departments actually release a letter of support in that way. And it makes me think that like when we actually go about, as physicists or geophysicists or as, a scientist in general, go about trying to like make these changes and knowing that we don't have the expertise and asking our colleagues in other departments to kind of lend us, from sociology or from gender, from, all the different types of departments, asking for their expertise to like help craft these studies and do it in a way that is ethical. I wonder just like, and this is really a well-formed question, just like to what extent like do we have the right to ask that of them when we very little kind of, we don't very often show up for them when it comes, when their time comes, when they need something. And so I kind of struggle with it a little bit because I feel like I have friends in those departments who are like, hey, like, if I ask them for, advice when it comes to designing a survey in order to better get an idea of our demographics in the department, I do that with the knowledge that when they asked us for something, we were not there for them. And it's just kind of, it's I don't know. I don't know if you have thoughts on that just in general. Oh, sorry, I think you're muted.
I'm muted and my cat is yelling at me. Okay, let me try that again. Sorry. So that sounds like an incredibly hard situation for everyone to be in. And I say that partly because this sounds like a culture thing. This sounds like something bigger than anything I have insight into and bigger than you. And it makes me wonder what interdisciplinary collaboration is like among these departments, if that's a thing that even exists, if there are like basic lines of communication, if the professors talk to each other. And this is something I know varies enormously between institutions. I've worked some places where the professors are all part of a union and they're into solidarity and support of each other's departments. I've worked other places where the like essentially tenured researchers want nothing to do with each other because they're all competing for funding. And I think it is really frustrating and sad to be in these kinds of positions where we are expecting the people who are more in charge and have more power to do something to help each other, to help us, junior researchers, students, grad students. But it doesn't seem like the architecture is there or the infrastructure or whatever it is that takes. I do want to note that when I talk about talking to sociologists, what I'm referring to is really asking people to do the thing that is their expertise. So when I say to a sociologist, I want to do a study of gender in STEM, and they say, I have a background in gender studies and survey design. This is a thing I can co-author. I'm not asking them to put their job on the line. I'm not asking them to have solidarity with me as a fellow employee. I'm saying, hey, do you want to get a publication out of this? And in some ways, that is a like fairly craven, narrow H-index defined kind of way to go around talking to people in other disciplines. But I honestly don't know what the answer is at a bigger level. I wish I had like a good straight answer for you. But it sounds like a kind of environment where like there's got to be somebody who has a friend in another department. That has to be a dynamic that exists somewhere. And that's got to be a start. That may be a place to build from. That may, oh my God, he's going to just scream now. It may be a place to try to build more constructive professional dynamics off of if those personal connections are there at all. But in the meantime, if you've noticed, and you have noticed really, that there's a dynamic where different groups are not helping each other, one of the first steps might be to just start showing up. Just say, all right, well, nobody helped us. We might as well start being the, oh God, I'm going to say the phrase, be the change you want to be in the world, and then I'm going to hate myself for it. But like, you kind of know where I'm going here, right? Like maybe the theoretical general you have to be the bigger person and be like, all right, well, you're not going to show up for us, but we know that this is the right thing to do. And we're going to volunteer at your event, and we're going to show up for your talk, and we're going to get involved in as many things as we can because we know it will enrich us as a community. And at some point, you're probably going to notice that we're doing it, and you'll know that this is something that means something to us. Yeah, that's all I got. I wish I had like a, magical solution answer. If he starts,
okay.
Sorry. I'm just gauging whether my cat is about to start doing property damage, in which case I will grab him and you will get to meet him. But that's kind of the part of the evening we're at.
Well, I hope he does do property damage then. I'm kidding. Okay, we are over time, but Dr. Strauss, if you're willing to stay, could we stop the recording and have people who might have been saving questions for after the recording is over to ask those? Is that okay? Okay, great. I'm going to stop the recording.